Hello students, today we're going to see how to prove root 2 is an irrational number. So most of the students are finding this difficult. Even the same difficulty was found by a person called as Euclid. So what did he do? He proved root 2 as an irrational number by proof of contradiction. He proved root 2 as an irrational number by proving through a contradiction. So what was that contradiction? So we know what is a rational number. Rational number are those numbers which are having p by q forms, correct? Say 4 by 16. Now here p is 4 and 16 is q. So 4 by 16 is a rational number. But we know 4 and 16 has 4 in common. So 4 ones are 4, 4s are 16. So p by q form of the same thing got reduced as 1 by 4. Now when I take HCF of p by q, HCF of p and q 1 comma 4 is 1. So hence 1 and 4 are called as co-primes. What are they called? As co-primes. Suppose if root 2 is a rational number, right? We cannot prove that anyway. So what he did is root 2, he assumed it as a rational number. He assumed root 2 is a rational number. When root 2 is a rational number, we know it has to be of p by q form. When root 2 is a rational number, we know it has to be of p by q form. When I send q the other side, then I'll be getting p is equals to root q. After squaring on both the sides, I've got p square is equals to root 2q whole square, wherein p square is equals to 2q square. So let us name this as equation 1. If p square is divisible by 2, then can I say p is also divisible by 2? Suppose say we have 2 square, right? It is 4. Now 4 is divisible by 2, meaning 2 is also divisible by 2, correct? If 4 is divisible by 2, then 2 is also divisible by 2, correct? So if p square is divisible by 2, then p is also divisible by 2. Hence, I'll name that divisibility as p is equals to 2k. So that I'll name it as equation 2. Now, by substituting equation 1 in equation 2, by substituting what? By substituting equation 1 in equation 2, I'll be getting, in place of p, I'll be putting 2k. So 2k square will be equal to 2q square, correct? Now, when we open this bracket, I'll be getting 4k square is equals to 2q square. Now 2 ones are 2 twos are. So what will I be left out with? Q square is equals to 2k square. Now again same logic comes. If q square is divisible by 2, then q is also divisible by 2, correct? As we explained previously. So if 4 is divisible by 2, then 2 is also divisible by 2, correct? Hence I can say q is equals to 2k dash. So let's name this as equation 3. Now when we are seeing equation 2 and 3, what can we find in common? Now if I say p comma q, if I write p comma q, I can say it as 2k comma 2k dash. What is common in between these two? 2 is common. So 2 will be our HCF. So what I can conclude is p and q has 2 as a common factor. That will be your HCF. When you have something other than 1, when you have any other HCF than 1, then that p and q is not called as co-primes. Hence, what did Euclid say now? If at all, if root 2 is rational, then it should have what? It should have an HCF of 1. It should have an HCF of 1, but it is not having over here. It is contradicting the statement of the definition of rational numbers itself. So if it is not rational, it has to be irrational, correct? Thank you. Hope this has solved your problem. Keep visiting us.